Welcome to Curiosity, the podcast where science meets wonder. Join us as we explore the fascinating, the innovative, and the unexpected, from the secrets of the cosmos to the marvels of everyday life. Each episode takes you on a journey to uncover the knowledge and stories that fuel our endless quest for understanding. Let your curiosity guide you. Melodies in numbers. Exploring the harmony of math and music. The relationship between music theory and mathematics is a profound and ancient connection that reveals the shared foundations of both disciplines in structure, harmony, and patterns. From the earliest civilizations, thinkers like Pythagoras explored how mathematical principles underlie the sounds we hear, creating a framework that remains central to music theory today. At its core, this relationship demonstrates how numbers, ratios, and geometry shape the way we perceive and create music, bridging the abstract world of mathematics with the emotional resonance of sound. One of the most fundamental aspects of this relationship lies in the concept of pitch and frequency. Musical notes correspond to sound waves with specific frequencies, and the intervals between notes are defined by the ratios of these frequencies. For instance, an octave, one of the most harmonious intervals, involves a frequency ratio of 2:1. Similarly, the perfect fifth, another foundational interval, has a ratio of 3:2. These ratios not only explain why certain combinations of notes sound pleasing but also highlight the inherent mathematical order in music. Scales, the building blocks of musical composition, also reflect mathematical principles. The widely used Western musical scale, the diatonic scale, is based on a specific sequence of whole and half steps that create patterns of tension and resolution. This structure is closely related to the overtone series, a natural phenomenon where a vibrating string or air column produces harmonics at frequencies that are integer multiples of the fundamental frequency. The placement of notes within scales aligns with these harmonics, demonstrating the mathematical basis for the tonal system. Rhythm, another fundamental component of music, is inherently mathematical as well. It relies on patterns of time division and synchronization, often described using fractions or ratios. For example, a measure of music divided into 4 beats can be further divided into halves, thirds, or quarters, creating diverse rhythmic textures. This interplay between temporal units gives rise to complex rhythmic structures like polyrhythms, where 2 or more contrasting rhythms are played simultaneously, requiring a deep understanding of proportionality and timing. The relationship between mathematics and music extends beyond these basic principles into more advanced territories. Concepts like symmetry, fractals, and group theory find parallels in musical composition and analysis. Composers like Johann Sebastian Bach incorporated mathematical structures into their works, using techniques like counterpoint and fugues to create intricate, balanced compositions. In the 20th century, composers such as Arnold Schoenberg applied mathematical ideas like serialism, a method based on ordered sequences of pitches, to explore new musical possibilities. This intersection of music and mathematics is not merely a theoretical construct but a practical tool for composers, musicians, and scientists. It provides a framework for understanding why certain combinations of sounds evoke particular emotions and how patterns in music mirror the natural patterns found in mathematics. In the next part, we will delve deeper into historical milestones, notable figures, and modern applications that continue to enrich this fascinating dialogue between music and math. The history of music theory's relationship with mathematics is a journey through time, shaped by the contributions of philosophers, scientists, and composers who sought to understand and formalize the nature of sound and harmony. The origins of this relationship can be traced back to ancient Greece, where Pythagoras discovered that the harmonious sounds of musical intervals correspond to simple mathematical ratios. This revelation, made using monochords, demonstrated that the beauty of music was not arbitrary but rooted in the logical structure of numbers. For Pythagoras and his followers, music was considered a reflection of cosmic harmony, intertwining their studies with broader metaphysical ideas. Fast forward to the Renaissance, and we find a renewed exploration of the mathematical foundations of music as part of the broader intellectual revival. During this period, theorists like Johannes Kepler and Galileo Galilei examined the role of proportions and geometry in music, linking them to the movements of celestial bodies and the physical properties of sound. Kepler, for example, in his Harmonics Mundi, The Harmony of the World, suggested that planetary orbits followed musical principles, an idea that influenced both scientific and musical thought. The Baroque period brought new advances as composers like Johann Sebastian Bach merged mathematical rigor with artistic expression. Bach's The Well-Tempered Clavier exemplifies this synthesis, showcasing the practical application of equal temperament, a tuning system that divides the octave into 12 equal parts, enabling instruments to play in any key. This system, rooted in logarithmic calculations, became a cornerstone of Western music, demonstrating how mathematical precision could expand artistic possibilities. In the 19th and 20th centuries, the relationship between mathematics and music evolved further, with composers like Frédéric Chopin, Arnold Schoenberg, and Igor Stravinsky pushing the boundaries of tonal and rhythmic structures. Schoenberg's 12-tone technique, for instance, used ordered sets of pitches to eliminate the dominance of a single tonal center, effectively reshaping the musical landscape. This technique is deeply mathematical, relying on permutations and transformations that ensure compositional coherence without traditional harmonic rules. Simultaneously, scientific advances in acoustics and wave theory deepened our understanding of how sound behaves. Helmholtz's work on the physics of sound waves clarified the relationship between frequencies, overtones, and timbre, bridging the gap between theoretical mathematics and practical musicality. This period also saw the emergence of algorithms and computing, enabling new forms of composition and analysis. By the mid-20th century, composers like Iannis Xenakis began using mathematical concepts such as stochastic processes and probability to create innovative works that blended sound with statistical modeling. As the dialogue between music and mathematics continued to evolve, it became clear that these disciplines were not just parallel fields but deeply interwoven realms of human creativity and logic. In the final part, we'll explore how this relationship manifests in contemporary music, digital technology, and scientific research, offering insights into both the past and future of these timeless connections. In the modern era, the relationship between music theory and mathematics continues to evolve, driven by technological advancements and new scientific insights. Digital technology has revolutionized how music is created, analyzed, and consumed, further blurring the lines between the two disciplines. Computers and software now allow composers and musicians to use algorithms to generate music, explore complex mathematical patterns, and simulate the physics of sound with unprecedented precision. One fascinating application of mathematics in contemporary music is algorithmic composition. This process uses mathematical formulas, sequences, and randomness to create music. Composers like Yannis Xenakis pioneered this approach by integrating mathematical models like Markov chains and probability theory into their works. Today, algorithmic composition is accessible to a broader audience through software tools that leverage artificial intelligence and machine learning, enabling users to experiment with musical creation guided by mathematical principles. Digital audio processing, another area where mathematics and music intersect, has transformed the way sound is manipulated and reproduced. Fourier analysis, a mathematical method for breaking down complex waveforms into simpler components, underpins many modern audio technologies. It is essential for tasks like pitch correction, sound synthesis, and noise reduction. These applications highlight how abstract mathematical concepts directly impact the soundscapes of our everyday lives. Beyond composition and audio technology, mathematics also plays a critical role in analyzing and understanding music. Researchers use mathematical tools to study the structure of compositions, uncovering hidden patterns and symmetries. For instance, group theory, a branch of abstract algebra, is used to analyze musical transformations, such as inversions and transpositions, providing deeper insights into the structural relationships within a piece of music. This interplay extends into neuroscience and cognitive science, where researchers investigate how the brain processes music. Studies have revealed that listening to and performing music involves mathematical cognition, as the brain subconsciously processes rhythms, intervals, and harmonic relationships. These findings not only enhance our understanding of music's impact on the human mind but also inspire new therapeutic applications, such as using music to improve mathematical reasoning or treat neurological disorders. Perhaps most intriguingly, the relationship between music and mathematics continues to reveal universal patterns that transcend cultural and historical boundaries. The same principles that govern harmony, rhythm, and acoustics are reflected in the natural world, from the spirals of galaxies to the oscillations of atomic particles. This connection reminds us that music and mathematics are not separate domains but expressions of the same fundamental truths that underpin the universe. The dialogue between music and mathematics is a testament to human creativity and curiosity. By exploring their intersections, we not only deepen our appreciation of both disciplines but also gain profound insights into the nature of reality itself. This enduring relationship underscores the beauty of patterns, the universality of structure, and the infinite possibilities that arise when science and art converge.